Hey guys, here's a quick little walkthrough of what we would call the comparison test. Sometimes it's called the direct comparison test. And the idea is simply this. You're going to take a series that you might not be able to determine convergence on and compare it to a series that you know convergence on. So whether it converges or diverges, and then we're going to make that comparison. Okay? So this is how you do it. Let's say you have a series that looks like this. And you're looking at it and you're like, it looks really familiar. I feel like, I could almost pretend that one isn't even there in the denominator and kind of figure out this series by itself and recognize it as that geometric series that we've done before. The problem is having the plus one in there, this isn't a geometric series anymore. If you were to list out the first few terms, you'd realize you can't get from one term to the next by simply multiplying by some, common ratio. So what we do is we compare it to a series that we do know. Okay, this series is geometric, and the R value is just 1 over 2, which we know an absolute value is clearly less than 1. So therefore, this series converges. So the idea is you want the series in question to either be smaller than a convergent series, because then it would converge, or bigger than a divergent series. If you have a series bigger than a divergent series, well, then that series would diverge as well. So that's the whole idea. It's a little manipulative. You have to be a little manipulating, I should say, a little creative sometimes in how you do it. But in the end, all it takes is a little recognition of, basic, inequality. Which one's bigger? If I have a bigger denominator here, even if it's ever so slight, this entire ratio is actually going to be smaller than this ratio. So the comparing works out to be that this series is actually smaller than that series, and the series over here we know converges because it's geometric with a common ratio less than 1, between -1 and 1. Therefore, this series converges, and we just simply say by comparison, or something like that, by the comparison test, by direct comparison, and it's with this series here. So that's the main idea for a comparison test. Okay, here's another one. And this one looks a little more complicated, but it's going to have a similar explanation. Okay, so you look at, you look at this one real quick, and you realize, there's no specific rule for this. It's certainly not geometric. Nothing I can really, tell right off the bat. I mean, again, the sequence has to go to 0 to have a chance. The sequence definitely goes to 0. But what about the series? So the way I always try to describe it is, let's try to compare it with something very similar to this as n gets really, really big. So as n gets really, really big, this plus 3 becomes pretty insignificant. Even the plus 4n becomes pretty insignificant. And all you're really looking at are kind of those, those sort of leading terms. This isn't much different than when we did straight up limits as n went to infinity and determined that, we could use the ratio of the leading coefficients, assuming they were the same. If the power in the denominator was bigger, remember that would go to 0. But all we're trying to do here is come up with some other series that acts like this series does as n gets really, really big. So I'm looking, I see the 5, nothing else can go with the 5, but in the denominator I'm just going to use the 2n squared. And then it begins to look like something I know how to do. I can do this one, because really this is just the same thing. If I pull out that 5/2, it'll look even more familiar. Hopefully you recognize that as a simple p-series. So if 1 over n squared is going to converge, well then multiplying that by 2.5 is certainly still going to converge, right? So this series converges because it is a p-series with, what's that, 2, p equals 2, which is greater than 1. So this series converges. So if all goes well, I should be able to justify that this series is actually smaller than that series, which should make sense if you look at it quickly, because again, we're adding pieces to the denominator. The numerator is the same, so there's no worry about which one's bigger there. The denominator, the first term is the same, but these two terms add value in the denominator, which makes the entire ratio actually smaller, so therefore this series converges by comparison. Okay? One more. How about something like this? Okay, so as n gets really, really big, this is the natural log of some really big number, so that's getting really, really big. The denominator is also getting really big, but I don't know for sure, what to compare it to right off the bat. Hopefully, well, first of all, you realize this series does go to 0, right? You can use L'Hopital. I think we've done that one before. So it passes our little gateway test, and so it has a chance to converge. Well, I'm going to compare it to the only thing that this looks like to me that I could possibly compare it to, and hopefully you're recognizing that also as the simple harmonic. Okay, so this series is our harmonic series, our straight up regular old harmonic, thus diverges. So in this case, because this series diverges, my gut is telling me that this seems to act a lot like this one, except it's got a numerator that's different than 1. In fact, the numerator we could compare to 1 and determine if it's going to be bigger or smaller. So what I usually say again is just think of the first couple of terms if you want. What if n was 1? If n was 1, you have the natural log of 1, which is 0. So this actually becomes 0, and that's smaller. Unfortunately, if you have a series that is smaller than another series, and the series that you're comparing it to diverges, well, we don't know for sure then what this series is going to do. So if you just did one term and gave up, unfortunately you didn't look hard enough, because remember, I don't care what it's doing at n equals 1. Yeah, that's helpful just to get an idea of the pattern, but I care what's happening as n's going to infinity. In fact, as you go to 2 and 3 and 4 and 5, something happens. There's a breaking point where these two series are actually the same. So it starts out as this series being smaller, but there's a breaking point where they end up being the same. What's the natural log? What can you take the natural log of to actually get 1? The natural log of e is 1. So the breaking point is e, but n can't be e because these are just integers. So really, when n is greater than 3, really greater than or equal to 3, this series is actually bigger when n is greater or equal to 3. Right? Because e is between 2 and 3. If n was 2, this would still be smaller, and that wouldn't help us. So all I cared about was what's happening to this as n gets bigger and bigger, and the moment we hit 3 or more, this series is bigger than that one. This one is a harmonic, which diverges. Our series is bigger than one that we know diverges. Therefore, this series diverges by comparison. And that's the idea behind the comparison test. Okay, so hopefully that'll get you through. If you need any help, be sure and ask, and I will make another video for the other test, the limit comparison test. Okay?